What is up, everyone? I hope you're doing well today. Today, we are going to be talking about the qubit and how it relates to Postulate 1 in much more depth. So the qubit can be represented formally as the function of some vector psi, which is an arbitrary wave or arbitrary state, is equal to the amplitude of one basis state plus amplitude of another basis state, where amplitude most often is ignored as a complex number. And we can see that when psi is the unit vector and a and b are arbitrary representations of complex numbers, which in those situations the complex numbers would be the amplitude, and that the states 0 and 1, which most often represent a bit, which we'll use for our qubit, form the distinguishable vector states for the qubit known as its orthonormal basis sets, or just the basis states. We'll begin by restating Postulate 1 because I believe the better that we understand the postulates, the better we understand the laws that these quantum mechanical systems must abide. Postulate 1 says that associated to any isolated physical system is a complex vector space with an inner product most often known as a Hilbert space, but we'll leave that out for now and we'll refer to it as the state space of that system. The system is completely described by its state vector, which is a unit vector in that system's state space. How does a qubit relate to Postulate 1 and how do we know it obeys this postulate? The qubit abides Postulate 1 of quantum mechanics since it can be described by its own inner product, where taking the inner product of psi with psi itself is equal to 1. Therefore, showing us that the probabilities of it being either 0 or 1 relates to a and b in such a way that taking a squared plus b squared results in 1, which means the qubit's got to be somewhere, or our states or particles got to be somewhere. When the inner product is equal to 1, we can see that a squared plus b squared is equal to 1, where a and b are the absolute values in these scenarios. This means that the vector space is normalized by the equation a squared plus b squared is equal to 1. Now, as I stated earlier, it means that the particle or state's got to be somewhere. Prior to measuring the qubit, it will not always be in the basis state 0 or 1. As we most often know, it'll probably be in a superposition of both the states. So it could be 0.1, 0.2, maybe it's actually 0, maybe it's actually 1, but we'll never know until we measure it. We use amplitude to consider the probability that one of the state vectors will appear upon being measured. Most often, it's 1 over the square root of 2, which means that there's a 50% chance of it landing on either of the two state vectors. The superposition of a qubit in its raw form can be described as the state vector 0 subtracted by the state vector 1 over the square root of 2. Or if you'd like to, complicate it a little more and see it more in depth, we can see that its discrete model is more so represented by 1 over the square root of 2, 0, minus 1 over the square root of 2, 1. I wanted to figure out why we subtract the second state vector from the first one. And in doing so, I ended up picking up an old physics book I never thought I'd touch and found out it has a quantum mechanics section. The state space or state vector 0 can be understood as Schrodinger's wave function describing all parts of the wave described by the cosine of kx minus wt, where k is Boltzmann's constant, x is some position, subtracted by the angular velocity at a certain time. On the other hand, the states vector 1 can be seen as the other side of this wave described by sine of kx minus wt. Schrodinger's equation helps us localize or create a particle in a box for sense. And this is really important when identifying the qubit because we want our qubit to be localized in some way. That's why the probability of a qubit leaving its superposition to land on 0 is 1 over the square root of 2, while the qubit leaving its superposition to land on 1 is negative 1 over the square root of 2. And this is important because it actually demonstrated the correctness behind the qubit and helped me better understand to a deeper depth that it abides these laws of quantum mechanical systems. Because we don't want to just blindly accept what's told to us. And most often, and I'm not saying that you shouldn't, you should take advice from anyone that's smarter than you because there will always be someone smarter than you, no matter how smart you get. But it's always important to ask questions and not to just accept things the way they are. Because if we do, we are just blindly following the people that tell us. Thank you guys for watching this video today. I felt like this was important and I felt like I got 1% better out of making this video. I hope you guys enjoyed it. I hope you guys learned a thing or two as well. I will be trying to get a whiteboard or a chalkboard sometime here soon. I'm still trying to figure out how I want to do, once it gets to more mathematical approaches, I want to figure out how I can approach it in such a way that you guys will be interested in learning it while I explain it. I've been holding off on buying the whiteboard for a little bit because I do want to plan that out a little better. Thank you for watching and I hope you have a good rest of your day. Stay learning.